Hello everyone, welcome to my new video in my Mathematics Essential series. In this video, I will continue proving trigonometric identities, and in particular, I will prove these two, trigonometric identities 1 and 2. And the first one, which says that the sine of negative theta equals negative sine of theta, says in function speak that sine is an odd function, and the second trigonometric identity, which says that the cosine of theta is equal to the cosine of negative theta, says in function talk that the cosine function is an even function. So I've never seen these names ascribed to these identities, parity identities, but I think they would be fitting names. Parity is basically a word that describes the evenness or oddness of a number. So for instance, 2 is even, we say that 2 has even parity. And if, since 3 is odd, we can say things like 3 has odd parity and 2 and 3 have opposite parity. And we can say that consecutive integers have opposite parity and things like that. So I think parity identities would be a fitting name for these identities, but for geometric reasons, they are commonly referred to as reflection identities. Okay, now I do want to tell you something that I think is interesting that I found when I was thinking about how I was going to prove all of these identities, and settling on the decision to only prove the 3 highlighted in green geometrically and then prove the rest just by applying previous identities. I did suspect that maybe it could be done that just by proving these 3 really powerful identities in green, 3, 10, and 11, that the rest could just be proved by applying other identities and doing algebraic manipulation. But then I ran into a temporary obstacle trying to do that. And I started to suspect that perhaps it couldn't be done because in order to prove these two here, 12 and 13, the difference formula, or the difference formulae, I felt like I needed 1 and 2. And in order to prove 1 and 2, I felt like I needed 12 and 13. So I was worried about a circularity issue. And I thought that, well, either I will have to prove these two geometrically and then prove 12 and 13, or the other way around. So either way, I would end up having to prove 5 geometrically before I could prove the rest just by applying other identities. But I persisted with it because I really wanted to see whether it could be done just by proving 3, 10, and 11 geometrically, and then proving the rest by applying identities. And it turns out it can be done, and I found a neat little proof. I found it myself, but of course, I'm not the first. This is just basic trigonometry, so I'm certain that this has been done many times before me, and even if it hadn't, it would not really impress anyone because it is basic trigonometry. So, but I am a little bit chuffed that I found this proof because it was a nice revelation to me as well. So let's get started with these proofs, and you probably haven't seen this proof because usually these two are proved first. So the two that I'm about to prove, these two are usually proved first in any class on trigonometric identities. And they are proved geometrically just with right angle triangles. But I will show you a nice proof. And what we will do is we will make use of the two sum, or just one of them. We will just use this identity 11, which is one of the sum formulae, the sine of theta plus phi, okay, to prove it. So I will write down what we are proving, okay? And it turns out from one proof, both identities will follow. Okay, so identities 1 and 2. Okay, so 1 says, I'm not sure whether 1 was the sine or the cosine yet. So the first identity is that the cosine of negative theta is equal to the cosine of theta. Okay, and the other identity is that the sine of negative theta is equal to negative sine of positive theta. Okay, so to put it rather crudely, you can kind of think of these identities as saying, look, when you are taking cosines of angles, you never really have to worry about negative angles because it's the same thing as taking the cosine of the positive of that angle. And if ever you're annoyed with a negative angle inside a sine function, you can just put that negative sign out the front of sine. Okay, so that's a crude way of thinking about these identities, but it's not inaccurate. Okay, it really does describe what you're allowed to do. Okay, now the identity that we will make use of. So this isn't the proof yet. I'm just going to talk you through some things to help you follow the proof. So we are going to apply one of the sum formulae. All right, which is identity 11. So the sine of theta plus phi is equal to the sine of theta, okay, times the cosine of phi plus the cosine of theta times the sine of phi. Okay, it might be a little strange thinking that we, how can we prove these two identities? Because there's no sums of angles going on here, at least not explicitly. Okay, you can think of, this as the cosine of 0 minus theta, but that doesn't really seem to help us. If you can hear that sound, that's an Australian bird called a kookaburra. Okay, they make that laughing sound in the morning. Okay, but one way I want you to think of this identity here, on the left-hand side, it says the sine of theta plus some angle equals everything on the right-hand side. Okay, so everywhere where there is a phi, I want you to just think of that as some angle. So I will write it like this. Okay, the sine of theta plus some angle. So I'll just leave some empty brackets to denote, quote unquote, some angle, which means on the right-hand side, we have the sine of theta times the cosine of just some angle plus the cosine of theta times the sine of just some angle, okay? Now, what if that angle was negative theta? Okay, well, it can be any angle. Okay, it's negative theta, right? Well, then we would be taking the cosine of negative theta here and the sine of negative theta here, all right? But really, what is this expression here? It's just the sine of theta minus theta, right? Which is equal to the sine of 0. And the sine of 0 just is 0. So really, we would have this entire expression equal to the 0, okay? And we could work on, we could subtract terms from both sides of the equation and so forth. So I'm going to leave that there. That was just some background understanding for the proof that I'm about to give. Okay, so proof. I'll start the proof now. Proof of identities 1 and 2. Okay, we're proving these two identities. All right, that cosine is an even function and that sine is an odd function. Okay, so by identity 10, which is the sum formula, or the sum formula for the sine of theta plus phi, we have, okay, well, 0 equals the sine of 0, which equals, well, 0 equals anything minus itself. So we can write theta minus theta, okay, which equals the sine of theta plus negative theta. Okay, and the only reason why I write in this step is just to explicitly justify the application of the sum formula, okay? We have a sum of two angles in here, theta and negative theta. So we are justified in using the sum formula, okay, which equals the sine of theta times the cosine of negative theta, this is by the sum formula, plus the cosine of theta times the sine of negative theta. Okay, but this is all equal to 0. Okay, so we really have this equation, right? I will change this to, an implication sign. So this implies that this expression on the right-hand side is equal to 0. Okay, so this all equals 0. Okay, so what we can do is we can subtract this term from both sides. And if we do that, we have that the cosine of theta times the sine of negative theta equals negative sine of theta times the cosine of negative theta. Okay, now what we can do is we can divide both sides by the sine of negative theta, or actually we can divide both sides by the cosine of theta and divide both sides by the cosine of negative theta after that. Now, whenever you want to divide both sides of an equation by something and then divide both sides by something else, you can do it in one step by dividing by the product of those two things that you want to divide by. So you don't have to do it in two steps. Okay, so we want to divide by the cosine of theta and then divide by the cosine of negative theta. So we'll just do that in one step by dividing by their product. Okay, and we have to do the same thing on the right-hand side. So we divide by the cosine of theta times the cosine of negative theta. Okay, and now you see that there's some cancellation, and you can probably hear that the kookaburras have started laughing again. It's kind of a natural Australian alarm clock, okay? But I'm already up. It's about 5:44 a.m. where I am in Australia. Okay, so we have some cancellation. These factors cancel. Okay, and on the left-hand side, these factors cancel here. So we are left with the sine of negative theta over the cosine of negative theta, which equals negative the sine of theta over the cosine of theta. Now, ordinarily, okay, you cannot, when you have a fraction on the left-hand side of an equation and a fraction on the right-hand side of the equation, you cannot go ahead and just claim that therefore the numerators and denominators must be equal respectively. So you can't equate the numerators and the denominators. That's not something you can always do. Okay, you can rarely do that when you're working with arbitrary expressions. Okay, because for example, well, this is a counterexample. Okay, 4 over 8, well, that equals 1 over 2. It does equal 1/2. But of course, the numerators are not equal. Okay, 4 does not equal 1. And the denominators are not equal. 8 does not equal 2. Okay, and the issue is that there can be common factors. So you can see here that with the fraction on the left-hand side, there is a common factor of 4 in the numerator and the denominator. Okay, but with the fractions that we have, okay, we don't have any common factors in the numerator and denominator on the left-hand side of the equation. We don't have any common factors in the numerator and denominator of the fraction on the right-hand side of the equation. However, what we do have is this negative sign. So the issue that this negative sign presents is that if we were to equate the numerators and equate the denominators, does the negative sign go with the numerators or does the negative sign go with the denominators? Okay, because, if we have these fractions a over b, okay, often you can just write the negative sign out in front of the fraction, or you can apply it to the numerator, or you can apply it to the denominator. Okay, they are all equal. Okay, so where does the negative sign go? That's the problem. Okay, and this is a common technique in mathematical proofs. Whenever you don't know which way something goes, you don't know which of how many cases are the correct case, you can split it into cases and see if you can exclude any of those cases and narrow it down. Okay, so we just have two cases. Okay, either the sine of negative theta equals -1 times the sine of theta. So basically this equation says either the negative sign goes with the numerators or the negative sign goes with the denominators. So the cosine of negative theta equals the cosine of theta. Okay, now, the negative sign going with the denominators. I missed the negative sign. So negative cosine of theta. Okay, now obviously one of these two cases hold. So either this case holds or this case holds. In other words, the negative sign goes with the numerators or it goes with the denominators. And of course, the clue as to which one you should exclude is in the equations that we are trying to prove. Okay, we are trying to prove these identities. So, that's a dead giveaway that the negative sign would go with signs. So in what we've done, it would go with the numerators. All right, but we have to prove that. So let's try and think of a way to exclude this case. Okay, and here is how you can exclude it. All right, so suppose it's the second case. So suppose the cosine of negative theta equals negative cosine of theta. Okay, then this must hold for any theta. All right, it must hold for any value of theta. All right, so if theta equals 0, okay, if this is true, it has to be true for theta equals 0. So if theta equals 0, then the cosine of negative theta, well, -0, because we're taking theta to be 0, equals negative cosine of 0. All right, which implies that the cosine, well, -0 is just 0 because it's -1 times 0. Okay, it implies that the cosine of 0 is equal to the negative cosine of 0. But the cosine of 0, so this implies, okay, the cosine of 0 is just 1. Okay, so on the left-hand side, we have 1, and on the right-hand side, we would have this -1 times 1, which would just be -1, right? Okay, which is a contradiction. And whenever you get a contradiction, okay, the assumption that generated the contradiction must be false. And what was our assumption? Okay, we supposed that it was the second case that held, that the cosine of negative theta was equal to negative cosine of theta. Okay, so hence, the cosine of negative theta does not equal the negative cosine of theta. Thus, it's the other case that holds. The sine of negative theta equals -1 times the sine of positive theta, which implies, I'll just write and, okay, the cosine of negative theta equals the cosine of theta. Okay, so this completes the proof. We can write a little square, which is always a nice feeling. And what is also a nice feeling is crossing things off a to-do list. So let's go up to our list of 19 trigonometric identities and cross off the ones we've proven. Okay, we've just proven 1 and 2. Okay, so that leaves 10 to go. So we're just about halfway through proving all of them. Okay, well, I'll leave it there. In the next video, I think I will prove the difference formulae. Okay, so if you enjoyed this video, feel free to give it a like or a share. Feel free to leave a question in the comments if you have one. And if you would like a notification when I upload a new video, just subscribe to my channel. Until next time, bye for now.